Okay, well, good afternoon, everybody, or good morning. I want to welcome all of you. My name is Hannah Rifai, and I am pleased today to introduce our seminar speaker. First, I want to acknowledge the sponsors of the seminar, the Department of Civil Environmental Engineering, the Hurricane Resilience Research Institute, and NCALM, the National Center for Airborne Laser and Mapping. We are delighted to have our speaker today, Dr. Zhaoqing Yang, and he is Chief Scientist of Ocean Modeling in the Coastal Sciences Division at Pacific Northwest National Laboratories. And he's also a fellow at the University of Washington, actually a distinguished fellow. And what I wanted to talk about was the idea that his research is really covering climate change impacts on coastal processes. And today he's going to talk to us about modeling fluvial and coastal floods in a changing climate. For those of you in the room, please feel free to avail yourself of the snacks in the back. If you're new to the building, the bio facilities are outside the door to the right. And if you don't mind to mute all your cell phones and devices so we don't disrupt our speaker. For all of you online, thank you very much for being here with us today. And we are delighted that you were able to join us. Unfortunately, we cannot offer you any snacks at this time, but we're delighted that you are joining.
I'm very happy to be here, and thanks Dr. Hongyi Li and Kennedy Rifai to invite me to give the seminar here. So yes, like what you see in the title, my talk will be focused on the modeling of fluvial and coastal floods in the changing climate. But my research portfolio actually covers a very broad range, so I will probably also talk about a little bit other areas at the beginning of my presentation. So yeah, here's the very brief outline of my presentation. First of all, I would like to introduce the national labs, okay, because I work for the Pacific Northwest National Laboratory, and then I will talk about storm surge modeling and in the different coastal environment. Okay, the first first I'm going to talk about the Gulf of Mexico, and also in Puget Sound. I don't know. Okay, and the last of which I will focus most of my talk will be on the Mid-Atlantic coast is the ICON project that Hongyi and I actually both working on that project. So, Department of Energy owns 17 national labs, and the Office of Science actually has 10 national labs. PNNL is one of them. There are other labs, and you can see from this map with different symbols. For example, the sponsor would be like EERE, the energy efficiency and the renewable energy, and also nuclear administration, right? Those are the weapon lab like Sandia National Lab and Los Alamos National Lab. So, PNNL, it's located in Washington, state of Washington. The main campus is in Richland, as you see here. And we have three remote offices, Seattle. SCRIM is the home campus of Marine and Coastal Research Lab, okay? And it has about 80 people in the Coastal Division. We have about 4,800 people in PNNL. Majority of them is in Richland. The Marine Coastal Research Lab's mission is empower science and energy, in particular marine energy, and associates the environmental impact and national security. So when we talk about national security, it's mainly again in the coastal areas. So here's just an image that shows that we have, a couple of some small research vessel and saltwater labs in the facility, and we actually own quite a large area of wetland and by a very beautiful inlet and the bay in the Washington coast, northern Washington coast. So, but my office is in Seattle. I'm not be able to manage. Okay, now it works. So I'd like to talk a little bit about the research, especially the project actually, or the research group I manage. This is a very loosely managed group. Okay, here's the link of my research project. So mainly in 3 areas, large areas. Okay, marine renewable energy is one area. Actually, PNL or in our division, we lead the national resource assessment for both wave and the tidal energy. And also we actually lead the ocean current, which mainly focus on the Gulf Stream under the Florida current. And then we started to work on the ocean thermal energy conversion. And also we work with the wind energy offices work on the offshore wind. So those are more on the marine and offshore energy area. And another large area, main focus area is the coastal hazard. I think that's more relevant to the Hurricane Research Institute here. And especially we try to look at the effects of climate, okay? So we don't particularly to look at, very accurate hindcast or nowcast, okay, for application-wise, but we mainly look at the uncertainty or the process mechanisms under changing climate. Okay, so we develop different modeling approach, especially look at some physical process. The third category will be the coastal ecosystem related. Okay, so that related to, for example, a recent project I have also funded by Department of Energy is the microplastic freight and transport. And another, actually, it's quite large project is macroalgae offshore production. Okay, so U.S. has, well, either the top or the second top EEZ compared to actually France. If they include their territory, French will be the first one. But we have a large EEZ. However, we only occupy probably less than 1% of the macroalgae production. 97% will be in Asia. Okay, China, I think probably more than 90% of the production of macroalgae. So why Department of Energy is interested in that? Ultimately, we want to look at the potential for biofuel conversion. Okay, but in the short term, of course, it has a benefit of food and the stock and also carbon sequestration. Okay, because you take up the CO2 and the sink to the deep ocean. So that is at least that's one of the concepts actually we're looking at. So I'm going to go through some examples. The first I mentioned about the Gulf Mexico storm surge. It's actually, this is mainly focused on a development of climate model, a couple climate model and a coastal model. So when we talk about climate model here, it's mainly we develop the dynamic, the downscale WRF simulation. Okay, so there's atmospheric simulation. So for storm surge, one is important mechanism is to have accurate private, wind forcing, right? So we can utilize the existing wind product, especially based on observation or data assimilation. But what about in the future? That's what we try to look at it. But I'm not going to go to too much detail on this. So the model we are using is FECOM final volume coastal ocean model, and atmospheric model is a WRF. So this panel upper right is coastal model grid, and lower right is the simulation of a WRF wind field. Okay. So we validated the model with actually 4 major hurricanes induce a storm surge. And here are the track. And also the time actually it happened. Actually, Katrina is of course it's one of the famous. This project actually we worked this 10 years ago. I don't know at that time actually you were probably still actually we working together. No, okay. So it's quite long ago. It's a real project. It's one of the multi-million-dollar project with Oak Ridge National Lab together. Okay, so. But we lead the coastal modeling project. So here shows, of course, when we develop a model, we always ask the question, okay, how accurate? And typically, we have a water level. Actually, today I talked to Dr. Lee. So he actually developed, I'm very interested in his work about using satellite data to mapping inundation area, right? Because this is something very, very important. We need to, don't forget, any model, we need to use data-driven to validate, right? So you can see some of the data actually during just at the peak of the surge, it stopped because the instrument get damaged, right? We don't have data. And the other data set would be the high water mark that's post survey. So people, FEMA collected those data. So this is a comparison. This is the model validation, and then we will use the model to project what would be the inundation or of coastal inundation and the future climate, right? When we talk about future climate, people very easy to think about it is the sea level rise. And there's also very important component actually in the relative sea level rise is the subsidence. So without any inundation, if the land sink, you also get inundated, right? You get submerged. So this is something we think it's important to take into account. And New Orleans area is famous because of that, right? So we actually, based on the Louisiana, there's an agency, I think a coastal protection and restoration authority, they produce some estimate of a land subsidence rate, and we use that to project that in 2100 and what is the land subsidence. So in the lower two figure, it shows with that rate, how much water actually land just under current water level, what the area will be underwater, okay? And then on top of that, if we run a similar Katrina in the future, what would happen? So this is mainly what it's like. Of course, the other thing is a sea level rise. So the upper right shows about 1 meter above current mean sea level. If let's say just use a bathtub approach, and that is the area will be submerged or inundated, right? So I'm not going to go to the very detail, but those image, the presentation will be recorded, but you can look at the left image is the current condition. Okay, on the right, the 3 panel basically shows the sea level rise condition alone, and with Katrina forcing. And the middle panel shows just the land subsidence of what it will cause. So, and the last will be the combined effect. So we actually published these 2 papers on this study. It shows it is a very strong linear distribution. It is not just on, you cannot add the 2 on top of each other. And it is also very, there's a strong variation in terms of spatial distribution. In some of the area, you're actually getting even drier. So it is definitely have impact in the different local area, okay? So those information, I think in the local agency of coastal planet, it's very, very useful. They actually take those information to into their climate adaptation or mitigation strategy, okay, development. So this is just something for fun, I think. It's a movie comparison. For the left is the current Katrina simulation, okay, inundation. The color indicates the water height. On the right is with only, I think it's 1 foot. It's a small, sea level rise in the future. How large of the area it will get more inundated compared to current condition. So I think when we talk about coastal or storm surge, we also think about, tropical cyclone, right? In Gulf of Mexico, mid-Atlantic, East Coast. And people really seldom to think about Pacific Northwest. However, Pacific Northwest actually subject, to very strong extratropical cyclones. Okay, those actually can bring up the wind as high as like a Category 3. Why is it so vulnerable actually in the Pacific Northwest? Because we don't usually have those, in terms of planning, right? Build the dike and the protection and those. So we actually experience a more frequent flood. It's not necessarily in that scale like here in the south or in Gulf of Mexico or mid-Atlantic. But more importantly, we have a very high tidal range. It's about more than 4 meters, and sometimes it actually is a 5 meter tidal range. But if you look at so this is in the middle 2 time series, actually directly from the NOAA gauge. Okay, those 2 lines are actually also from 2 lines from NOAA gauge. One is measurement, the other is just a tidal predicted water level without any storm surge. So you can see in the lower right is in the middle one is water level induced by Hurricane Ivan, and the green shows the storm surge, right? Very distinct, you can see the signal. And the tidal range is about ½ meter. But in the middle, and you can see very high tidal range is about 5 meter tidal range during spring. And you can hardly to see the storm surge signal, okay? But actually it's get flooded, okay? In many of the area. And it is a very famous actual windstorm. And if we filter out the tidal range, the tidal signal, and then you immediately see the signal, okay? This is the red line. So it's about a 1 meter a surge there. So, so we developed the model for the entire Salton Sea, and this project actually is funded both. I think it's NOVA through Washington Sea Grant. Okay, so we compare model to the data, and you barely can see the difference. Right, model is blue, and the data is a red dot, and top of pretty much on the blue line at all the station in the Puget Sound. But this is a storm event, and we really cannot see where's the storm, right? But if you remove the tidal signal, then you see it. Okay, it's about, it's not very high compared to here, but it's still high enough, 2 to 3 feet, okay, of storm surge. So it says, if windstorm, and usually the windstorm is always happening in the holidays, so that it's also caused a lot of damage, and so like the snow, it's usually associated with the heavy rainfall and the snow. So it's here you probably not experience that much in terms of the snow, but probably not nowadays. Climate and everything now just very, very challenging, right? So some of the things we don't encounter before now, actually we have to take into account. So we actually simulated the 34 top historical windstorm event induced storm surge in the region. This is just another 2 examples. One is called White Christmas snowstorm. It's very huge storm, bring a lot of heavy snow and cause the area because of, lost the power just because of wind and the snowfall. And you can see actually in the region, the storm surge is very, very different. So we actually do an ensemble of 32 top storm surge, and just look at all the storm surge, look at the maximum, and we generate this map and provide to the state of Washington and to guide in terms of, extreme event induce a storm surge, and the future climate. So, Now, next I'm going to talk about this is the main focus of my talk. It's the Integrated Coastal Modeling Project, or it's called ICON. It's funded by DOE, Office of Science. The program is a BER, Environmental, Biological and Environmental Research Program, but it's multi-program actually under the BER. So University of Zhaoqing is one of the partner, and PNNL is the lead institute, and co-lead with Los Alamos is another, but multiple national lab. Okay, and we utilize the DOE's supercomputer at the different national labs. So, okay, let me explain this very high level on this project. We basically look at key process and uncertainty. Okay, key process, here we talk about atmospheric, ocean, and the land. So naturally, we will think about it, this is Earth system modeling, right? And our long-term vision is to deliver a robust, predictive understanding of the coastal evolution of that accounts for complex and multi-scale interaction among the physical, biological, and human systems. So it's basically consists of all the elements in the coastal zone. So that's why we have how many? I think 14, many institutes, okay, together on this project. And it is multi-million-dollar project. We are still in phase 1, and it's already 3 or 4 years now. So yeah, it is a big effort, and it's until recently DOE starts to really invest in coastal research, because in the past it's been really focusing on Earth system model development as a global model, larger scale. Okay, and so it is a direction I think it will be benefit to more actually connected to all the different institutes. And of course, here, national labs take the leadership here. So I mentioned about the different program actually support this research. So we select the Mid-Atlantic study region. Okay, there's some background about this, why it is important, of course. But I think I would like to focus on the research area here. So one is there are 4 funding program. Okay, one is the regional and global model and analysis. It's called RGMA. This is one program area, and multi-sector dynamics, which what I actually involved is the coastal hazard modeling. Okay, that actually more directly connected to the human system infrastructure and those. And the third element is the Earth system model development, and that is like the E3SM. If you have, I will mention that later. Again, it's more for the model development itself. Okay, it's Earth system model, and later on, actually not at the beginning, but later on we brought in got the support from the subsurface biochemistry program. Okay, so it's under groundwater. It's important. So I think you also work on that. At least the model you develop try to account for that, right? So, and we create one more research area is a cross-cutting, which just tied to because all these programs they are interacted. So it's short. So this last actually I also involved in that is in this program, and the cross-cutting is to try to understand some of the process actually interact with all these phenomena. Okay. So I mentioned about the study area, and specifically today, and the title back to the title of my talk is of fluvial and the coastal flood, right? So when we talk about fluvial, it means we need to account for the hydrology, the stream flow. And for the hydrodynamics, we consider 2 components. One is the coastal, the other actually is the urban flooding. Okay, so we have a 3 model in this task. One is DHSVM, and sorry about the acronym, but I will explain this later. But so here's the domain. So the green line on the right is the watershed model. And on the upper left panel, that's the blue. So that is the coastal ocean model. We extended the model much further out so that we can simulate the wind, I mean the hurricane or the tropical cyclone, right? Far from our model focus area. So the other is called the rift, which is urban area, and that lower right, lower left, the white color actually is the Philadelphia urban area. So I'm not going to go into the detail, but here's the name, the distributed hydrology soil vegetation model. It's actually developed by someone in PNNL. It's a widely used model. It's a two-dimensional model. It's 90 meter resolution, okay, runs at every 3 hours. So this model provides stream flow, actually fits into the coastal ocean model, okay, so as an upstream boundary condition. And here is the storm surge model we developed for the Delaware Bay, and the resolution is about from 10 meter in the stream area to 30 kilometer in the open boundary. Okay, and then right now we use a reanalysis wind field, okay, error 5, and we consider tide and also stream flow from DHSVM. So the error 5 is mainly provide wind field. So here's the grid zoom in the Delaware Bay and some of the, okay, one thing I want to point out, if we use the USGS gauge, that's typically most of the, I mean, at least in the past, to fit the model as upstream boundary condition, right? Use the stream flow. But we don't have a gauge in many of the small stream, right? And they are important, especially for wetland flooding. So the DHSVM actually has 162 outlet, okay, stream outlet connected to the FV to coastal model. So that's, you can see how the comparison we account for, even though it's small, but the wetland is important in terms of stream flow. This is the rift, it's the rapid infrastructure flood model, flood tool. Okay, I don't know much about this. It's one of the components that we have a separate team member to work on it, but it's taken to rapid precipitation, heavy rainfall. This is the main flooding, factor, but also river discharge, and also downstream take the FVCOM model actually as the open boundary condition. So wherever the open boundary, they will take these two model, DHSVM and FVCOM model to run this rapid flood model. Okay, so this is on the left, lower left is an example of the maximum flood depth in Philadelphia. I want to focus a little bit in the latest slide on the compound flooding. Well, compound, which means if you have at least two, okay, compound processed together, on top of each other, or co-current, then this is how we define it. It's mainly driven by storm surge from the open ocean. The surge from the coast, and the other is a heavy precipitation that actually is through hydrological model and the river runoff, right? So now there are quite a number of historical events actually happened in the mid-Atlantic, right? For example, Isabel, that is quite long ago, more than a decade, and Hurricane Irene also induced severe storm surge and also compound flooding actually from upstream. Sandy is famous. It's because it's so huge, right? Spread most of the East Coast and from the Gulf. So we actually look at how we define compound. So this 4 panel, it's basically look at the 99th percentile of water level, okay, flooded water level at the Newbold tide gauge, which is quite upstream, and also 95 top percentile in terms of stream discharge. So what we really looking for the signal, it's in the upper right quadrant. So which means it has very high stream flow, but also have a high water level storm surge from the coast. So the red color represent Irene. Okay, so you can see green is sandy. So sandy actually has on the horizontal, you can see there's some very huge, actually large area or a large value, but in terms of precipitation or stream flow, it's quite low. So it does not really cause compound flooding. So that's why we choose Irene. Okay. And we validate the model. This is just an example of the model validation of the DHSPM, the hydrological model. Okay. And yeah, so actually all these are already published, and the model validation actually is quite good. So very important, and well, we don't particularly tune the parameter. So it's very important is to have the high resolution, but also DEM. Okay, you need to have accurate DEM, and the grid need to really represent the physics of the DEM. You just cannot just blindly to have a high resolution. You have the connectivity right. So there's some indeed, you know, technical scale need to put it into it. So this is a 10 tide gauge, you know, NOVA tide gauge, and you can see, especially in the upstream, in the top two panel, you can see not just surge, but also river discharge sustain. I mean, the flood actually prolonged quite long. In the lower two panel actually is more in the entrance of the Delaware Bay. And you can see just after a day or two, and it's back to the normal, okay, after the storm should pass over. But in the upstream, actually the river, it become important. River discharge cause flood, the fluvial flood. And this is just another example of model validation. We validate not just water level, but also current. Current is important, you need to do it right, and I will show why later, okay? And I mentioned about data. It's important that this is a high watermark. Unfortunately, we don't really have any high watermark data on the New Jersey side. We were able to get on some data from Delaware side, the coast side. So it's also very challenging because the high watermark is post storm event, right? So the accuracy is also, you know, sometimes it has uncertainty in the high water marks. I think this is animation. It does not play, but okay. So, well, this is just an animation of the event, and basically you can see all the stream actually we take it into account, and also not just along the channel of the bay, but actually there's a significant transverse variation. Actually, Delaware Bay, Delaware coast will subject more flood actually in terms of risk to the northern side because of you know, the tropical cyclone, right? So the wind actually is blow towards you from the, when it's make landfall, it's blow towards your left, so pile the water more out to the Delaware coast. Let me explain this. So I probably should go fast a little bit here. So I talked about compound flooding, right? Coastal and the fluvial flooding. And so let's look at this event. Again, it's the same Irene event, but let's look at this two period. One, the block here shows is before the extreme river flow, but it's during the storm surge event at the entrance of the Delaware, and the second period actually is in during the heavy discharge period. So the left panel shows, okay, the flood during right before the peak of the river flow. So you can see the flood everywhere. This is the maximum flood water depth. It means the deviation from the mean flow, mean water level. Okay, so you can see an area actually here, and near Philadelphia, actually it's higher than both sides. But after the hurricane make landfall, then you follow with a heavy rainfall, and most of the region actually is already back to normal sea level. But in the upstream, way upstream, you still see a river flood impact. Okay, so okay, so now we want to investigate. Okay, what if the impact of antecedent soil moisture and also sea level rise on the yes.
How do you apply storm surge? It's an interface of river and the ocean. How do you apply storm surge as a boundary condition?
The storms, yeah.
It's got some height.
No, we actually storm surge. We basically use the wind field, and the wind actually will simulate. Basically, we're able to simulate the hurricane, right? So that's how it's generated the wind, the surface surge, and then the boundary is a way out. So yeah, I don't have an animation, but actually, if we have the animation further out, actually the surge actually is a propagate from offshore towards the coast. Did I answer your question?
Maybe a related question will answer. So in the FE form, you're solving shallow water equations.
Yes.
So when you, and it is on the river, not necessarily on the ocean. The shallow.
It is.
FE form.
Yeah. No, this is the bigger domain. It's actually much further out to the open ocean. So actually, it's a 3D, but it's still solve the the shallow water equation. So okay, yeah. So yeah, this is just a picture shows the soil moisture content during the Irene event. Because of time, I'm not going to go to the detail, but mainly we want to really investigate is what if the soil moisture have an impact on the flooding. Okay. So this is mainly from the hydrological component. Okay. Actually, I want to explain this a little bit more. So the red here, the bar chart is represent the precipitation, daily precipitation. So, and you can see the corresponding soil moisture content also related to the precipitation. Okay, daily precipitation. So we actually do a sensitivity with different soil moisture. We actually found that during Irene, the soil moisture is pretty much saturated. It's actually 95%. So we just do a sensitivity, give a different soil moisture and run the DHSVM, the hydrological model. Okay, and from 80% and every 5% increment, and we can see for different soil moisture, then the flux, actually the river flux will be different, right? Because you have a lower soil moisture, actually more infiltration, the rainfall will to the ground. So you actually don't have that much surface runoff. So your flood will be less. So that's mainly the concept here. So we investigate. So like we actually we expected, so let's just focus on these two top panel. So we during the storm surge, and this is the flood water depth, and the red is the Irene, actual Irene. All the dashed line is corresponding to different soil moisture. So when you have lower soil moisture, actually, your flooding will be less because of due to the stream flow. Okay, but if you look at this area, it's actually this is the compound effect. Okay, you actually have a flood elevation actually is more than both sides of the river. Okay. So that is very interesting, and I think that's one of the major findings. This is basically shows the same thing, but from a horizontal view. Okay, so again, it's 95%, which is corresponding to Irene. You have an area here in the middle panel here, so it's got flooded some more. Okay, now let's look at the sea level rise scenario. Okay, so we consider sea level rise condition, and we based on the NASA observation for the historical event, over the last 40 years, and consider different climate scenario. Okay, so basically what we seen here is under future climate condition in general, we will see a more area got inundated, which we all know. Okay, but the key is here, we find it's very interesting, the compound actually disappear in some way here, right? So the black line is under future climate condition, which would cause a sea level rise. The reason behind this is once you have, okay, that's actually ties to the tidal dynamics. So when you have a large flood area, more than the existing condition, a lot of the shallow area actually get flooded, and it's damp, actually, the tidal amplitude. So the interaction of the tidal component versus the flood actually becomes smaller. So that's why we don't see it here. But if the sea level rise, right now we consider sea level rise actually even for the conservative for 2.6 scenario, it still costs about 0.7 meter sea level rise. But if we consider less than 0.5 sea level rise, or just 20 or 30 centimeter, then you will see the compound actually more close to the Irene case. Okay, finally, I would like to just mention a little bit the ongoing and the future research also under ICON. And so I mentioned about the ensemble, the E3SM is the energy exascale Earth system model. So this is a model led by Department of the Office of Science and has been heavily invested, right, over the years, and many national lab and also universities have been working on this, and we also contributed to the river routing model, so which is a very important component. So we want to look at, okay, can we use this global model to project future climate, especially hurricane, right? So this is just a sensitivity, and we initialized Hurricane Irene event with E3SM. Basically, just a few days ahead, initialize a different environment, which it's not my field, so our collaborator from Leno, Los Alamos, to produce this ensemble 50 event, and then we run the model, use the wind field they produce. So the red or pinkish area actually shows the range, right? So that is the uncertainty, in the future, but it shows the range more or less actually similar to the mean is similar to the Irene, which is the black case. It's a little bit higher, but it seems can get the physics right. So it's encouraging. So in the past, it's pretty much the global model, Earth system model, they develop their own model, do not really connect to the very fine resolution local model. Okay, that's something we try to do. The other is we will try to simulate long-term simulation actually into the future. In the past, storm surge is very expensive to run, and usually people just run a few days, maybe weeks, and 1 month is the most. We don't barely run like 1 year, right? Because you just focus on the hurricane season. Here, we actually try to run it continuously for 80 years. So where we got the data. So we got the WOOF simulation for this TGW data set. Okay. which provide the meteorological forcing. Also, not just the wind, but also precipitation, which drive the DHSVM, which is the river flood. I mean coastal, not coastal, hydrological model. And that will give the upstream boundary condition to drive the storm surge model. And this is the WRF simulation domain. And because it is not as out as our regional domain, so we actually have to modify our domain and just within the WRF simulation, so we can get all the wind field. And actually, the TGW WRF simulation, we compare their simulation with Sandy along this NOAA meteorological gauge station. Actually, you can see they capture all the process. I mean, the wind field speed quite well. Okay, so this gives us some confidence in terms of using the model to do our simulation. And the other things that I mentioned about the future climate, it would be open boundary condition. So right now we just finished 40 years of a simulation. Okay, from 1980 to 2020, and the use this is, I believe, it's NOAA satellite data. There's a trend and a wave so that we can get to those data, but for the future, okay, I don't have the future slide, but for future, we actually would like to use the IPCC AR6 sea level projection. So we are constructing our future forcing now. So we are going to run, the next 40 to 80 years into the future. So this actually costs a month of a simulation on the supercomputer for us to run. So this is something in the Delaware Bay. I mentioned about temperature. I mean, not temperature. Current is important. This is a simulated salinity plume or freshwater plume, right? So I mentioned about the water quality is important, and shellfish, right? Oyster and those levels. So people actually really develop their own model, and then we try to leverage what DOE has invested and use the global model forcing and to drive the local model. Okay, so actually we actually prepare a manuscript. The model results are quite well actually compared to data salinity intrusion. So finally, I just want to mention about this is my last slide. So some opportunities at PNNL. This is particularly I hope is interested to young scientists, engineers. There's a distinguished postdoc fellowship which is open year-round, and all field, actually not just coastal. You can apply and look up the online. The other is for undergraduate student. It's called SULI. This is a DOE program, but sit in the different national lab. And the PNNL is one of the lab manage this. We also have a project-funded internship, and I want to mention that the internship, it's not just postdoc. Actually, it's a postbac, postmaster, and I hired them before, and at the end, we actually converted to a regular staff at a different rank, different level. And currently, actually, we have a full-time job opening. Well, just an opportunity, not try to do too much of advertisement here, but yeah. And finally, I would like to acknowledge our sponsor and many contributors to this presentation. Thank you.
So before we take any questions, I wanted to kind of set the background for our invitation, not only because he's a distinguished speaker, but several of us in the room have a grant with PNNL or funded by DOE to encourage collaboration between the University of Houston faculty and the national laboratories. And this is our first step to invite you all to not only take advantage of some of the opportunities, but actually to engage with scientists from PNNL and other laboratories. So Dr. Hong Yi Lee, can you stand up, please? He is the PI of the grant, the collaborative grant that we received. It's a modest grant, but really the intent of it is over the next couple of years to bring in speakers and for some of our faculty to visit some of the national labs and discuss sharing research ideas and potential collaborations. So we'll be sending out hopefully some of the opportunities, especially for student internships and work opportunities once you graduate with the national laboratories. There's quite a bit of interest to engage between U of H and not only PNNL, but the other national laboratories. So with that in mind, we'll take some questions from the folks in the audience in the room, and then we'll try to give our colleagues online a chance to ask some questions. So, go absolutely.
Thanks for your talk. In fact, my first student is now a scientist at PNNL. His name is Martin. Maybe you may not know, he works on climate. So
Yeah.
a couple of questions. First question is just I'm trying to understand these three ports, how the communication occurs between these three ports. First port you have is FECOM. I'm assuming it's a shallow water, basically flooding model.
Yeah.
Then you have a hydrological model. What process you have in the hydrological model? Darcy's equation, evapotranspiration.
It's a hydrodynamic model, so yes, it's also well. I don't know. Maybe Hong Yi know what's about the hydrological model. Yeah, it's also solved. It will produce a velocity, water level, and it's also have a interaction with the subsurface. It also consider snow melt and all those.
Surface and subsurface interaction also.
Right. Yes.
Okay. Then what about the rift model? What does it do?
That actually is the urban flooding model, right? So it's basically the main input is the directly heavy precipitation into the ground, and yeah, I think there's probably other function like
Okay, that's fine. That's fair enough.
yeah, I don't know the detail. Yeah.
Just curious.
Yeah.
So the related scientific question here is, you said you do uncertainty quantification if you are interested or group is interested. But especially when we deal these kinds of problems, there is so much uncertainty. Even if we take permeability of the soil, with the soil,
Right.
the permeability right here could be different from even a mile from here.
Yeah.
So how did you do this uncertainty quantification of this very big global model?
This is interesting and also very tough questions. So let me answer from a different perspective. So yeah, to reduce uncertainty, of course, even though I'm a modeler, I always promote measurement of data, right? Data is important. See if we can reproduce. So if there's some mismatch, then it will help understand what is the uncertainty. In some way, to minimize uncertainty is important, but the more important is where's the uncertainty come from, right? So it will help you to, for example, design your experiment or numerical experiment to do a series of sensitivity to look at the uncertainty. So today I talked to I don't know if he's one of the so he actually asked me, okay, I think his field is uncertainty analysis, right? So I don't know, there's some of the algorithm and to do it systematically, but to me, I feel understand that the physics in between is more important in some way. So
last question.
Yes.
You said you want to predict the hurricanes, at least I heard that, but hurricanes are also triggered by the difference in temperature in Atlantic and Pacific and all kinds of stuff.
Yeah.
But I didn't hear any, let's say, temperature differences or energy balance.
Yeah. Those are actually, we do not simulate the hurricane, right? The hurricane is simulated through the global model or atmospheric model, which take into the couple atmospheric and ocean model, which take into the heat exchange and the upper layer, thermodynamics. So we use the wind field from the atmospheric model. Okay, we do not simulate. Yeah.
If I could bother you to go back to slide 32, I have a question about the soil moisture.
Okay. This one?
Yeah, that one. So what this graph is showing us is that there's basically with a 15% difference in soil moisture, we have a very significant, like almost 80% reduction in the peak flow. Is that correct?
Yeah. So just think about it, that this is the soil moisture actually is for the entire watershed, right? So a lot of the water actually is being to subsurface. So if you have a more saturated soil, the flood actually the stream flow it's collect all the water into a narrow stream. That's why the water level is much higher.
That makes
Yeah.
sense. Have you looked at, you mentioned that Irene was very saturated. Have you looked at other potential hurricanes in the area for like a validation of this?
We haven't. Yeah.
The other question that I had was related to your, you showed a sea level rise map. Towards the end of your presentation, it was based on satellite altimetry. I think it's on slide 42. But have you looked or thought about perhaps propagating that uncertainty in the sea level rate changes for your, or is that something that you're planning on doing for your long?
Again, it's a sensitivity, right? If you look at the IPCC, the projection, you will see the uncertainty, the error bar is huge. So probably whatever we have a variation here is always within that range. So yeah, there's we don't specifically right now, we don't look at it. So, but keep in mind, we do aware there are all different factors and play into account in terms of uncertainty, especially projection out to, right, 80 years, so in the future.
Just one final question. So, we you have a lot of interaction with academia, obviously, but you have a lot of other cross-governmental work. I imagine that, for example, NOAA is working on their own models and that kind of thing. So we work on that with them.
The Puget Sound work actually is funded by NOAA, right? And I also in the past I also have coastal POCA. Actually, it's a POCA program. It's under NOAA. I actually have quite a lot of funding in the past and funded by NOAA. And currently, I actually have 2 proposals actually with NOAA. So I also have a project with EPA. So right now, the NOAA project is more tied to the climate because my research focuses more on the climate. But in the past, it's more like green infrastructure. Those things are actually small applied type.
Well, thank you so much. It was a fantastic presentation.
Thank you.
Other questions from the audience?
You showed us the modeling process, how the future Katrina will hit the studies. So basically you said that there was a sea level rise plus the land subsidence. So I'm just confused. So we see that there is pretty bigger surge will hit the land. But what kind of the level you consider like in the future Katrinas? Because also Harvey was pretty bigger and more make more damage. So like in the future it should be just worse and worse.
Okay, actually, it's a very good question. So this is indeed a very good question because we to be honest, right? Research is research. It does not really mean you can always get the result of what you expected.
Yeah.
Okay, we do have to be honest with that, right? So I mentioned about ensemble simulation. It's actually so challenging, and we at that time, that's a 10 years ago's project. I think it's ended, But anyway, but at that time we try to simulate do a long-term simulation with dynamic downscaling, and we actually found we were expected to see more stronger hurricane, but we would not be able to find it actually, right? So, but you are right. So there's also, and it's happening, in different areas, but I'm not a climate scientist, and also, but indeed, we face that challenge because, we were not able to run the simulation with initialization of the current climate and run into the future. it's maybe there's some limitation or to dissipate it, or I don't know. So I was not able to. Yeah.
Basically, there could be like, two modelings make it like the worst scenario where there's the biggest sea level rise and the huge lands of cities, and see like, okay, we will lost the 5 meters of the land, so everything is going to be flooded. Just move in the in the middle of the United States, then we will be safe. So, but I mean, there could be several.
Yeah, I surely understand. I mean, that is indeed something remain. I think I think probably different agency has a different focus, and then this project is mainly focused on how we can use the future climate model. Can you simulate a hurricane? Right, and can we use the simulated future hurricane to drive our model? That is the focus instead of, even though of course the motivation of background is about coastal planning and those, right? But I know many other universities actually in the region, actually they have a very detailed and fine, like the Excel group, right? Excel model, they actually have, so good simulations there. So
Thank you.
To add on to that previous question, I remember for the model up north, you added several different snowfall events and whatnot because that was common in the area. And I wanted to ask, recently, say in like Texas, we're seeing winter storms, for example, which we might have not seen 10 years ago.
Mhm.
Is there any interest in like revisiting this project and incorporating these previously unforeseen climate anomalies? Or
Yes, of course. Then this is a question to DOE program manager. No, I'm just, what I mean is this is a very high level question, right? Whether yes or no, I think this project right now is the focus of the Mid-Atlantic, right? We did talk about, okay, whatever the approach, actually some of the phenomena we see here, is there anything actually we saw in other region, or can we apply this approach to other regions? So Gulf of Mexico is a region actually being brought up. So
Just to add on top of that, my short answer, I simply understand, I could be wrong, is actually yes. Because those kind of unforeseen, never seen before type of extreme event is part of climate change. So in order to better deal with climate change, we have to get ready to deal with this kind of extreme event we never seen before.
yeah.
I have two questions. For example, if you look at the picture on the left, I was wondering, how did you determine how far upland or upstream the FPCOM model, the mesh for the FPCOM model,
Yeah.
is going to go? I mean, are you going to go towards the rivers? How far are you going? How did you?
Yeah, this is good modeling questions. Usually we take the model. FVCOM can actually simulate the river flow. Oh, okay, all the way. So, and how upstream, we usually take it up to the station that without any tidal signal, and at the state USGS gauge station. This is the usually we stop there because we can use USGS flow gauge to drive the model, but also have the hydrologic model output to compare at the site, right? So this one we stop at the Trenton. It's because there's a fall there. There's basically no tidal can actually further propagate. So we take, and there's a gauge there. So, but in general, this is how you should do in terms of modeling, a coastal modeling. Take the upstream boundary condition as far as you can, that without any tidal influence, so that you don't stop somewhere that actually you will miss the interaction between the stream flow and the coastal process could be important.
And then in the Delaware Bay, did you notice any tidal amplification throughout the river because of the changing bed elevation and the tidal amplitudes?
I do not fully get your question. You mean changing the bed elevation?
No, I mean, the tidal amplification
Oh.
due to the interaction of the riverbed.
Yes.
The tidal.
The geometry, right, is something, play a very important. It's not all the estuary or river will have the tidal amplification, but bottom friction is the one thing, and we have a paper published that actually just look at the nonlinear interaction. There's a node point in the somewhere between Wellington and Philadelphia. I believe actually the tidal amplitude become a minimum there, and then amplify again. So yes, so it is an important phenomenon. So
Other question?
My question is on the compound flooding simulation.
Mhm.
So when you simulate these floods, there are infrastructures, mitigating infrastructures just built for flood protection, for example, right? So at the same time, there are also policies that are developed against these as a mitigation measure against these type of floods, right? So when you simulate them, for example, after a major event, particularly those kinds of events can affect policy changes or mitigation measure changes. And do you account for these things when you simulate them over a long period of time, like the risk management strategies that are put in place? At the same time, how do you see the efficiencies of these kinds of mitigation measures on the future resilience of the community as a whole against these type of risky events?
I personally haven't really looking into how affected through the mitigation policy and those things. So, but the one I think that we have enough. Other projects that related to that. For example, dam operation. For example, that's one thing. Okay, and then in other region, it's related to fish migration and those. So I don't know whether that will answer your questions. So, but we try to make this data in general, especially NOAA funded data. It's community, a stakeholder and outreach engagement is one of the priority, right? So we use to work with the local governments to provide useful data to them. So not sure that answer your question. So, but in our modeling effort, we do not directly, take those into account.
I also got a technical question regarding modeling. I know we have when we would have a flood event, we have some water from the watershed toward the ocean, right? And also we have this tidal effect, have the counter direction from the ocean to the inland.
Yeah.
So I'm assuming that we are solving the shallow water equation with some gravel method, right?
Mm-hmm.
And how the model handling, for example, we have a counter direction flow. When they meet each other, there will be some energy dissipate, right? How the model counter this part?
Okay, so that actually the last slide I show actually is the salinity, right? So one is just gravitational also, right? So, but there's another actually in the estuary we are talking about. Actually, your question is more related to estuary plume. Actually, the dynamics. So when I've talked about shallow water equation, so yes, actually it's more hydrostatic, right? Assumption equation. So it actually is a three-dimensional. So we take into account the density gradient. So you will have the fresh water more light on top of the water column, okay? And the bottom layer will be salt water, so that intrude into the estuary. The reason actually now I want to answer back to the question, tied back to the question next to, next to you is, we simulate the salinity, the salt water intrusion. Actually, we work with the state government of Delaware, and they actually have an intake drinking water intake somewhere upstream. And there's a one time in the history they got during very drought condition, actually they got salt water into the intake. So they want to understand what in the future will look like. So the model itself will take into account those processes. It's called the two-layer circulation, okay, indirect, and the salt water will intrude during drought. But we also try to look at, okay, in a flood event, they push the front much further out, and how long it adjusts the back, because wetland habitat is very important. They survive in certain salinity regime. Actually, in the Pacific Northwest, there is some flooding when very salt water come in, and all the plant die because it's salt water. So, yeah, that's why it's important to simulate not just a storm surge, which it's called barotropic, is the gravity wave. So, but also a density gradient induced circulations.
So I want to give an opportunity for our colleagues online to ask questions. So anybody online would like to ask a question, unmute your microphone and ask your question. Doesn't look like we have any questions online from our participants. So let's give another round of applause. Thank you very much for an excellent talk. And thank you, audience. On your way out, please grab a water and a snack. And we appreciate very much your attendance.
We have